Yeah, let's continue. Okay, let's consider EDTA titration curves in detail. Okay, let's look at this figure first. Yeah, this is general EDTA titration curve. Okay? Usually, you this titration is done in a way that you you know, you make a solution. Yeah, you unknown solution. You take a unknown solution, and then that's the analyte. Okay, and then in burette, you add the standard EDTA solution. Yeah, with an exactly known concentration. Okay, and then you add EDTA solution, drop by drop into the analyte solution, and here as you add the EDTA solution, and then something changes. So which one? Which, which one do you think is changing? This is the metal ion concentrations, okay? So usually in EDT titration, the y-axis is what? Metal ion concentration, but we take uh, logarithm of this one and put the negative sign here. This is kind of pH, okay? But in this case, instead of proton concentration, we use metal ion concentration. So we write PM, okay? This is called P function, okay? Here it's a PM, all right? And then, just like X-base titration curve, the PM doesn't change much. And then around this equivalence point, there is a sudden change in PM. It suddenly increases, all right? Increases. And then after this equivalence point, this increment becomes slower. Okay, so from this EDT titration curve, it is very easy. Okay, very easy to identify the equivalence point. Okay? Or you can differentiate this curve to find the equivalence point. Either way, you know, and this one. So we write. You can we divide this titration curve before the equivalence point and at the equivalence point and after the equivalence point. Okay, as usual in um, like in S-based chemistry, right? All right, let's consider here. And as I said, this one from now on, since we are working at a constant pH, we use the conditional formation constant metal ions and EDT, makes this complex, and we use Kf prime. So region 1 is a before equivalence point. Here in this region, excess metal ions still exist because not enough EDTA is added. Yeah, so there is still excess. I mean the free metal ions in the solution. Okay, and then this one we simply assume that free metal ions from the dissociation of metal EDTA complex is negligible, right? And at the exactly equivalence points, which one? And look at that, this one. Yeah, you the moles of free EDTA and free metal ions are the same, so they makes this one-to-one complex. Yeah, so we can simply say that in solution there is only metal EDTA complex. Yeah, not much. Actually, very negligible amount of free metal ions and EDTA are present in the solution. Okay, and what's the free metal ion concentration? By the way, and then we have to consider this reverse reaction. Although little, anyway, there are the metal ions present in the solution. Okay, so this is dissociation of this complex gives free metal ions and free EDTA. Okay, and then here, since it dissociates by 1 to 1, okay, in 1 to 1, so this one, their concentrations are the same. Okay, very easy. And then what is the free metal ion concentration after the equivalence point. Yeah? And then here the excess EDTA exists, yeah, beyond this point. So using the excess EDTA, yeah, excess EDTA is a free EDTA concentration, and then use what this formation conditional formation constant. We can easily calculate this free metal ions. And this one, although the moles of uh, metal EDTA complex is constant, but as you add more and more EDTA, since the volume increases, the concentration of this complex, yeah, becomes smaller and smaller. All right. Okay, let's take an example here. Again, now let's consider this calcium, the titration with EDTA. In original solution, you have 0.04 molar calcium of 50 milliliters, okay, which that solution is purported at pH 10, okay, and the concentration of EDTA, this is the standard EDTA, right, is 0.08 molar. And the first thing we have to do is to find the conditional formation constant using this one. This is alpha 4 minus, and this is the formation constant, and we get 1.34 times 10 to 10, okay, and also you have to find the equivalence point. Okay? That is very easy because there is a one-to-one complexation. Okay? So a number of moles of calcium and a number of moles of EDTA are the same at the equivalence point. Yeah? So from here, uh, we usually calculate VE, yeah? Which is 25.0 milliliters. Okay, from here, since EDTA concentration is twice of the calcium concentration, so required EDTA volume is just half of original calcium volume, right? Which is 25 ml. Okay, now consider when you added 5 milliliters of EDTA, and what is the calcium concentration? Well, the 5 times, let me see, 0.08 molar, right? That's the added EDTA mole, right? And that by that amount, calcium ions are removed by calcium EDTA complex. So since we are calculating the remaining calcium ion concentration, so we have to what this way. Anyway, the textbook way is a little bit different, from my way. But my way is that doing that. First, original calcium ion moles is calculated. Okay, 50 times 0.04 and minus, okay, added EDTA moles, which is 0.5 milliliters and multiplied by 0.08, okay, and then divide the total volume, yeah, which is 50 plus 5, okay, that way. But this way is a little bit confusing, yeah, confusing at least to me, but it's up to you. Yeah, you follow the textbook way or my way, your professor's way. Yeah, it depends upon you. Okay, anyway, let's look at that. Yeah, this is the initial fraction, okay, a remaining fraction, and original concentration of calcium, and then this is the volume, what the correction, okay, dilution factor. And anyway, that way we calculated the free calcium ion concentration uh, to be 0.0291 molar. Okay, so P calcium value is 1.54. Okay, and then you may wonder, oh, professor, why don't you calculate the initial, P calcium? Okay? That's easy. You simply take the negative logarithm of this concentration, but it is not shown here. Okay, okay, this way, we can calculate the P calcium value before the equivalence point. And then let's move on to uh, the the equivalence point, region 2. Okay, and when 25 milliliters of EDTA is added, we reach, okay, theoretically we reach the equivalence point. And then this one, calcium ion EDTA complex concentration is what? Simply the half, right? Oh, not half, I'm sorry. We have to consider the volume increase, right? This correction factor. Okay? Anyway, this is initial concentration of calcium ion, and then multiply by 50. That's the initial volume of calcium ion, and then divide by what? Total volume, which is 75, and then we get 0.0267 molar. Okay, and then now we go further to calculate this free calcium ion. Okay, and now we start from here, and then by x and x it is dissociated, and then this one concentration a little bit decreased by x. Okay, and then from the conditional formation constant, yeah, this is important part. Okay, to use this equation you have to use the conditional formation constant here. Okay, yeah, this one it is given by this way, and then simply we we can solve this equation, and then we get calcium ion, free calcium ion, yeah, which is the same as the that of free EDTA concentration is 1.4 times 10 to minus 6 molar, and P calcium becomes 5.85. All right, and then now after equivalence point, now consider you just added 1 milliliter more past equivalence point. Okay, and virtually all metal ions in the form of this calcium EDTA complex form, and the excess amount of EDTA is just simply 1 millimolar. Okay, and then we usually calculate the free EDTA concentration. Okay, 1 milliliter divided by 76, that's the total volume, and original multiplied by original EDTA concentration, and the answer is 1.05 times 10 to minus 3 molar. Okay, and then this one calcium EDTA complex also easily calculated. Okay, and we consider the volume change. Okay, and 0.04 molar, right? This original calcium concentration multiplied by original calcium volume and divided by total volume, and which is 2.63 times 10 to minus 2 molar. Okay, and also we use this equation again, and we know this calcium EDTA complex concentration, and this EDTA concentration also calculated here, and calcium free calcium ion concentration becomes quite low, 1.9 times 10 to minus 9 molar, and then P calcium value is 8.73. Okay, now let's look at this curve. Yeah? Here, this one, the black line is the titration curve, and then you do that kind of calculation all along the this EDTA volume here, right? Yeah? And that is very cumbersome, very nuisance, time consuming. But you'll see soon that how we construct this total, the metal EDTA complex curve, okay, titration curve, just like in acid-base titration curve. Yeah, we can apply same concept to here. Anyway, look at that. So as we expected, the P M value, the P metal value increases slowly, and then suddenly increase quite much, okay, quite a bit around the this equivalence point, and then passing the equivalence point, the increment becomes also slower, right? And this is the titration curve. And but what about the different metal ions? Okay, like strontium, divalent strontium ion here. This is the shown in a blue curve, and only difference is the what formation constant. Okay, strontium ion and calcium EDTA formation constant is smaller than calcium ion, but still very large. Okay, and then smaller. We don't know yeah, how small. Yeah, we have to look up the table. Uh, but well, let's see, just a smaller, right? And then the small effect now appeared here by the small what this jump distance. Okay, this is kf prime at the pH 10 for this strontium ion is 1.6 times 10 to 8. Okay, this one. And since this is quite small, not quite, maybe 100 times smaller than the calcium case, and then this part before the equivalence point, same curve, yeah, we obtain, and then it suddenly jumps. Okay, but this jump distance is smaller than the calcium case. Okay, so here we can conclude that the better titration curve is obtained with high formation constant. Okay, with a high formation constant. So if we, the formation constant is really high, and then this jump is becomes very high, and that means that we can lower the solution pH. Okay, you understand, right? So if this formation constant is really high, yeah, and then yeah, it is possible to do to get this kind of a nice titration curve even at very acidic pH. Okay, that's the beauty of EDTA titration. All right.